Hi everyone, my name is 𝙍𝙤𝙗𝙤𝘾. My teammate is Braden. We are from Chuan Presbyterian Secondary School. I'm 14 years old this year and we are participating in the NRC CoSpace U19 category, and there is 3 challenges in total. The challenges consist of 3 roads that I have to complete. For this challenge, it is crucial for the robot to trace lines at fast speeds without oversteering or understeering at turning points. For color detection, it is important for us to set the range of colors like blue, red, and green to tell the robot what it needs to do next. The result is to complete the points on the map as fast as possible and achieve a superb score. At the heart of it, simulating robots allows for testing and refining their behaviors in various scenarios, which helps identify potential issues and optimize performance before deploying them in real-life situations. Our game plan is to develop an autonomous bot that can navigate through a map by utilizing color sensors and line tracing technology. The primary objective is to enable the robot to independently move around the environment by detecting and following the lines marked on the map. These lines serve as guides for the robot's movement, with the color sensors continuously scanning the area beneath the bot to identify the path. As the robot detects these lines, it will adjust its direction and speed to stay on course, ensuring navigation throughout the map. By using these approaches, the robot will be able to maneuver autonomously, avoiding obstacles and following predetermined routes without any human intervention. This approach not only enhances the robot's efficiency but also opens up possibilities for various applications where autonomous navigation is crucial. There are 4 types of sensors on the robot: ultrasonic sensor, gyro sensors, infrared sensors, and RGB sensors. Ultrasonic sensors measure the distance to an obstacle, like a wall, by emitting sound waves and calculating the time it takes for the echo to return, enabling precise obstacle detection and distance measurement. Gyro sensors track rotational movements and changes in orientation of the robot by measuring angular velocity. Infrared sensors detect the presence and absence of white lines on the track by emitting infrared light and measuring the amount of reflected light. RGB sensors identify the differentiate colors by analyzing the intensity of red, green, and blue light components, facilitating color-based object recognition. Here are key points of how steering works on a 2-wheel robot. Differential steering. The robot uses differential steering where the speed and direction of each wheel are independently controlled to achieve movement and steering. For straight movement, to move forward or backward in a straight line, both wheels are driven at the same speed and in the same direction. For turning left or right, to turn the robot, the wheels rotate at different speed for a right turn. The left wheel moves faster than the right wheel, and for a left turn, the right wheel moves faster than the left. In-place rotation. The bot can rotate in place by driving the wheels in opposite directions. For example, turning the left wheel forward and turning the wheel backward. The right wheel backward will cause the robot to rotate clockwise. Curve navigation. Smooth curves are achieved to gradually adjusting the speed difference between the 2 wheels, allowing the robot to follow a curved path rather than making sharp turns. The tracking algorithm is based on a sensor input. The control system adjusts the robot's motor to steer it back on track if it deviates from the line. The feedback loop This process forms a continuous feedback loop of 20 to 40 frames per second, with the robot constantly making small adjustments to maintain its alignment with the line. Navigation. The robot uses this method to follow the line accurately, navigate turns, and stay on the intended path. Color space. Color detection. RGB color segmentation analyzes the red, green, and blue components to identify the differentiate colors based on their intensities. Thresholding. It uses specific threshold for each color channel to classify objects or areas into color categories, allowing for precise color-based decisions. Real-time detection. The system enables immediate response to detected colors, which is essential for tasks to make decisions. Color calibration. If the color sensor senses red that is more than 20 and green is less than 250 and blue that is less than 20, then the left wheel will move at speed 30 and the right wheel will move at speed 10, which causes it to make a 90-degree right turn. We also use state machine for task 1. State changes. A state machine switches between different states, like modes, based on certain rules or events. For example, a robot might be in a moving state and switch to a stopping state when it hits an obstacle. For output actions, the actions or output of the system depend on the current state. For instance, the robot is in the moving state. It might make the wheels spin. If it's in the stopping state, it might turn off the wheels. Predictable behavior. State machines help make systems behave in a clear and predictable way. Since each state and transition is defined, you know exactly what the system will do next based on its current state. This is what I gave that can be applied to the real world. Color segmentation concepts can be applied to detect traffic light signals, and IR sensors can be used to line tracking robot in factories, as it can help to shift large and heavy objects around the factory. State machine can be used in cooking robots of a washing machine to help wash your clothes. We have seen some AI in our daily lives, such as ChatGPT, Siri, Copilot, and some of them are even in our apps. We can also see AI in YouTube when we search for a video. It will try to guess what you are searching for based on your search history.